Jason Blau. I'm the interim chair of mechanical engineering, engineering mechanics. And I have the honor today of introducing our speaker, Dr. Brad King, who is faculty in our department. He got all of his degrees from University of Michigan, Aerospace engineering. Then he held a postdoc position at NIST and came up here to Michigan Tech in 1999 and has been a professor in our department since. He started one company, astrophysics, for a while, and then he moved on and started Orbion in 2016. And he's going to talk today about Orbion. One of the other things that he has done in our department is he's the advisor for our Aerospace enterprise, which is a group of students. So our enterprise, the students can get involved second semester, freshman year, and stay involved through their senior year. And they design and build satellites. So Michigan Tech has one satellite in space, one that's been launched. There's another one that's getting finished up now, hopefully for a launch, it sounds like in early 25. And Brad continues to advise that enterprise, as well as he's the CEO and founder of Orbion, and which makes ion propulsion for satellites. And with that, I'll turn it over to you, Brad.
What if you could count all the cars in Walmart's parking lot every single hour and keep a list of that, right? That's pretty valuable consumer information. Now, I'm not just talking about Houghton's Walmart up here. What if you could count the cars in every Walmart parking lot, everywhere on the face of the globe, every single hour? That's massive information. You can do that now with satellites. There are a number of companies out there, Planet Labs, Black Sky, Capella, ICEYE, where anybody with a credit card has access to satellite intelligence, just like only the USSR and the United States did back in the 70s and 80s. But it's bigger than counting cars. What if you could inventory everything on the surface of the Earth that's larger than 40 centimeters and track its movement and its instantaneous location? That's coming next. You're going to have a search bar for the Earth. Alexa, how many oil tankers sailed through the Straits of Hormuz yesterday? What were their names and how deep were they floating in the water? That kind of big data intel is coming within a few years. How are you going to get the information? Very soon, the other 3 billion people on the planet who don't have internet are going to be connected like a light switch without ever digging a trench or laying a fire. And that's what I mean by the small satellite revolution. This is being driven by satellites that range from about the size of a loaf of bread to about the size of the dishwasher in your house. And they're taking over the planet. I want to show you what today looks like. Let's put it into motion. That's right now. Over the UP, you can see, if you look very closely, a few little dots. There's a bunch of satellites up there. Doesn't look entirely impressive. Step back a little bit here. Now we're starting to see a few more show up. Let's move them a little bit more quickly so we can pick up their motion. Let's step back. What else can we see in here? Let's look for some features. Here, right here, is a Starlink train of satellites. Here's another one and another one. Those were launched within 2 weeks ago, 60 satellites at a tranche, and they haven't yet had time to spread out. So you're seeing them march along in a train. You can see another Starlink train right here. If you're out at night at the right time, you can see these trains. Let's keep moving out. Here's a special orbital band called the Molniya orbit, which is particular to Russia. It serves their very northern regions very effectively with communication satellites. Let's keep zooming out. You can see the geostationary communication satellite ring starting to show up. That outermost ring is a special orbit where a satellite takes exactly 24 hours to go around the Earth once. So what that means is the Earth is rotating underneath it at the exact same rate. So when you're on the Earth looking out, from your vantage point, the satellite never moves. It's just sitting in one spot in the sky. And that's some very expensive space real estate. Bring these back. speed them up. And that's happening right now. This is the satellite revolution, and we're just getting started. Let's look at how we got there. Here's a plot of space launches as a function of time, starting from the inception of the space age over in 1957. USSR surprised everybody and threw Sputnik up, and the race was on. And you can see the space race starting to grow. You can see the United States quickly outpacing Russia with launches per year. Then we're kind of tailing off. We had our heyday in the 60s and the 70s with the Apollo program. United States slowed down a little bit. Russia slowed down. The world picked up. But what you want to notice there is across the globe, up until about 2012, human beings launch about 150 things per year into space. Now I'm going to click on the next one and bring it to this year. The entire graph that I just showed you is on the bottom lines there. So we went from 150 things going up into space every year to thousands of things going up into space in a heartbeat. And this exponential curve is just getting started. Why did it happen? Well, there's no single story for why it happened. But if you go back to, say, 2001, people were passionate about space. We grew up in the Apollo era. We saw people on the moon. Space is very cool, but it was really hard to get there. Access to space was expensive. Only nation states could do it. It took a long time. You had a lot of engineers that would spend their entire career and work on one satellite if they were lucky. Because it was so hard to get to space, people were looking for innovative ways to get there on the limited rockets that were going up. And a craze called the nanosatellite boom was started by Professor Bob Twiggs in Stanford. He had a senior design class and they designed satellites. Well, for 20 years, they designed satellites. It was a paper tiger. You'd write a report and you'd be done. And he wanted to find ways for his students to get satellites into space. So he realized that the launch vehicles were going up, had unused mass on them. They could carry some things if they could fit. So he went out to Walmart and he bought a Beanie Baby, which was all the rage, and he gave it to his students, and it was a one-semester challenge to design a satellite the size of a Beanie Baby cube. Because if they could do that, he could find places for that on launch vehicles. And that then became a standard called a CubeSat. That's still around. At the same time, in 2001, you probably remember this when Google Earth came out. I remember being overwhelmed. You could pick 2 or 3 cities on the earth, London, New York, Rome, and zoom in and look at the streets. And oh my God, this is amazing. Wow. But they'll never do it for the whole globe. They did. But that opened up our appetite for geospatial intelligence and the thought of what could we do if we get all of this. A guy named Elon Musk was frustrated because he couldn't get to space either. So he said, to hell with it, I'm going to build a company that can do it on my own. So he founded SpaceX in 2002. So this was all an angst of how do we get into space more quickly. Then the consumer electronics revolution came along. Everybody wanted an iPhone in their pocket. And what that did was that drove the rapid development of small, cheap, reliable, low power electronics to drive the consumer market. And that had the effect of flipping the space development cycle on its head. We always heard about NASA spin-offs. An astronaut needed a drill for the space station. So NASA developed one, and 5 years later, every dad was getting one on Father's Day. And they needed smaller computers to get to the moon. And 10 years later, everybody's playing Pong on their Commodore VIC-20. So it went from space development to the Earth. Well, this flipped it on its head. All these engineers who wanted to get things into orbit who needed small satellites saw this wealth of consumer electronics that had giant terrestrial markets. They said, I can build a satellite out of the same stuff that's in that iPhone. So the ingredients were there for building these satellites. In the meantime, SpaceX finally got up. After 6 years of struggling, they got their first rocket off the ground. Then there was kind of a pile-on effect. All right, well, let's all come up with a way to buy a rocket and split the fare and put all of our small satellites on one rocket. That was called rideshare. In the past, it was one rocket, one satellite. So it was like a limousine. This was like a city bus. So rideshare was born, which opened up the floodgates. It led to, this record has since been broken. In 2017, India set a record with 104 satellites on one launch. That's been broken since then, but that shows what rideshare is going on. And then there was an idea for internet in the sky. If we could get thousands of satellites up there, why can't we use the satellites to provide internet instead of building towers and digging trenches all over the globe? Now, where are we? Bank of America Merrill Lynch has named space the next $1 trillion economy. We have a new branch of armed forces called the Space Force. We've got thousands of satellites up there right now giving you internet wherever you are. And the unanticipated benefits are still out there. And the best example I give is GPS was developed to help military navigation. The internet was helped to develop scientists collaborate over across the ocean. And the iPhone was developed so people can talk. Those three things in a vacuum, nobody saw Uber coming, right? All of a sudden, those three things come together, and these are the unanticipated benefits that are still out here from the space side. As I mentioned, Starlink, I've got Starlink at home, 3,000 satellites in orbit, give you internet anywhere you want that you can fit a dish this big and look at the sky. OneWeb is following closely on their heels. They have over 600 satellites in orbit. They're going to compete with Starlink. Amazon Kuiper, a guy named Jeff Bezos, is about to launch 13,000 satellites and make sure he gives Elon a run for his money. So filling the sky with internet satellites is starting. Our country, we're going to use space to keep us safe from bad guys. The Space Development Agency is developing a number of layers, they call it. They're developing a tracking layer, which is hundreds of small satellites that can pick up missile launches and hypersonic launches and track them. The data will then be sent to a transport layer, which will be thousands of small satellites that relay that data across the globe and get it back down. And then a custody layer to make sure they know everything that's going on. So in the past, our government has built these, what one general called big, fat, juicy targets. You had this one school bus sized satellite, you were just begging the enemy to come and poke at the eyes. And now we're to thousands of satellites because you don't have enough bullets in your magazine to take them all out. And this is going to revolutionize space defense. And this market that's inflected is going to be inflected again. The giant launch vehicles that are going to further disrupt it have yet to fly. The first one, we call it the Starship Singularity, just this past spring, had a mostly successful launch, but it's just one of a few. There's over 40 rocket companies out there right now developing rockets. New Glenn is developing a giant new rocket. Rocket Lab is coming up with a big one, and the Starship is coming along. And where Falcon 9 can launch about 60 Starlink satellites, Starship can take 300 of them at least 1/10 of the cost. So that inflection you've already seen is just the start. And this is what's driving it. I love this infographic because it's dense. Over on the left axis are the blue dots. That is the cost per kilogram to put something into orbit, right? It used to be very expensive. Down in 1960, it was $200,000 per kilogram to get something up. But as our technology improved, the cost came down, 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 down. Now we're down here with the SpaceX Falcon 9, that's about $3,000 per kilogram. And as I said, Starship is going to break that. If you believe Elon, it's going to be around $100 per kilogram. Whether that's true or not, it's still pretty good. So what happens when you reduce the barrier to a gold mine? The miners show up. The purple are the number of active satellites in orbit. You can see them completely following this curve, this reduction in cost. So this is just getting started. All right, talking about the overall market, I want to talk about Michigan Tech's place in this right now. And as Jason pointed out, we have an organization here called the Aerospace Enterprise. This is a group of about 100 undergraduate students from all different disciplines, mechanical, electrical, computer science, physics, all the way across campus. And the goal is to give these students an experience as if they're working for a space company, designing, building, flying satellites into orbit. 3 satellites I'm going to talk about. Oculus ASR was already launched. Oculus is Latin for the eye. This was a satellite designed to help imaging. I'll tell you about its mission. Oris is Latin for the ear. It's a satellite that's designed to eavesdrop on other communications. And Stratus is a cloud image. I'm going to go through each one of these in turn. So first, Oculus, right? So there's a lot of stuff up there. We as a nation need to know what it is, where it is, who owns it, and what's it going to do. So the way I talk about the Oculus background is I talk about the inverse dragon problem. So first I have to talk about the forward dragon problem. The forward dragon problem is if you're given a dragon, you know everything about the dragon, and you know what the environment is, can you predict what its footprints look like? And you can. You know how heavy he is, which way he's walking, how long his paces are, how soft the ground is. You can calculate what that signature will look like. The inverse dragon problem is a little bit harder. Come upon a dragon print. Is there anything in that print that can tell you what the dragon looked like, what it was doing, and where it might be going? So that is analogous to observing satellites and trying to determine features in what you can observe that tell you what the satellite is and what it's doing. And that was the Oculus mission. So space situational awareness is a term that the government uses to describe their desire to know not only what's up there and where it is, but who owns it, what it's doing, and what it might do next. And that's the key. The easiest way to do that is to look at stuff, get a telescope and look at it to see what the satellite's doing. But the problem is satellites are a long way away. So if you view a big satellite with a really big telescope, you can see everything about that satellite from Earth. There's not a lot of those telescopes around. On the left is a great big telescope on the top of a mountain in Maui and a great big satellite. It's the International Space Station with a space shuttle orbiter docked to it. And from that image, I can tell which way that satellite is pointed. I can tell what it's doing. I can tell if a door opens up, if a door closes. So that's great. The problem is I can only do that when that satellite happens to be over Hawaii. And that's a handful of minutes a day. So I want to know this all over the globe. I can't build satellite telescopes like this all over the globe, but hobby grade telescopes are very prolific. As the satellites get smaller, or the telescopes get smaller, or both, all you can see is a dot. Right? If you've been out at night, you can see a dot of a satellite going by. Go and grab a really good telescope from Walmart, damn thing still looks like a dot. So it seems like there's not enough information there to know what is the satellite doing, how is it oriented, but it turns out that there is. So the Oculus satellite was designed to be a viewing target for the United States Air Force at the time, now the Space Force. The idea is it is a satellite that can change its shape on command. It looks different from different viewing angles. And now the government observers can view this satellite and determine whether they can figure out what it's doing. And then we can tell them what it was actually doing. And then they can sharpen their pencil and do it again, and do it again, and do it again over a number of years. So for instance, if the Oculus is showing you its blue side, the dot's going to look kind of blue. If it's showing you its yellow side, the dot's going to look kind of yellow. So even though you just have a dot, now you have some information of which way the satellite is pointing, which is important. If you have a satellite with a camera on it, you want to know which way that camera is pointed. So if you know the outer reflectivity of a satellite beforehand, you can look at the dot and have some information about how it's pointed. You can tell if it's moving. If the satellite is spinning, you're going to see that dot flicker, bright dim, bright dim, bright dim, bright dim. And by the speed of that flickering, you now have information about how fast it's coming. If you know it's an 8-sided satellite and it's rotating, you count the flashes, divide by 8, there's the rotation. So the point is there's a lot of information you can get, even though all you can see is a dot. So the students here designed and built the Oculus ASR. And then it was taken down to a mountain facility in Albuquerque, New Mexico at Kirtland Air Force Base. And the Air Force cheated. They put the satellite on a robot arm. Down one leg of the tunnel was a big mirror that reflected the New Mexico sun on the satellite. Down another big leg of the tunnel were a whole bunch of imagers. And they held the satellite in every possible orientation with respect to the sun. So they had a map of how that satellite looked from every possible angle. So that makes it pretty easy when you're on the ground, you already have a map. China's not going to be so nice to let us take their satellites, look at it from every angle, get back, say we're good to go. But it gives them a database to start with to calibrate their models. So then what we did is we launched that satellite. And we were lucky. The launch ticket we pulled was on the second launch of the then most powerful launch vehicle on the planet, the SpaceX Falcon Heavy. So this thing has 3 Falcon 9 stages bolted together, 27 engines, makes 6 million pounds of thrust. And there's our cute little Oculus tucked inside the launch stack with 60 other satellites. So that is the stack of all the other satellites that went on it. And down in the lower left, you can see the Oculus. It has its odd 8-sided shape with a 4-sided shape. So that when it rotated, it gave a different flicker signature. And it went up and then deployed off of that. We went down with a team of students, many of whom had worked on it 6 years ago, who brought motorhomes and family down. And we had a great viewing party down there. And this was in June of 2019, and watched that thing go up, and it was amazing. If I didn't work on space before that launch, I would quit everything I was doing and work on space. It was unbelievable. The Earth shook. I can't even explain. All things come to an end. This past February, Oculus turned in Stardust. There's its altitude plot. There is drag in space, and Oculus did not have propulsion on it. So it was at the mercy of drag, which eventually made it spiral down, spiral down, spiral down. And then it comes in and burns up in the atmosphere. So on 20 February of 2023, just this last February, Oculus became Stardust. She's no longer with us. It was a good journey. Next satellite I'm going to talk about, Horus. That cool picture is not Horus, but it's important for understanding what Horus did. So not only do we want to know what's up there and what it's doing visually, these satellites are out there transmitting and broadcasting radio signals that have the potential to interfere with each other. If you're a satellite company, you have a license to transmit Ka band to the city of Philadelphia. If somebody's next to you overlapping that beam with theirs, nobody's going to be able to get the signal. It has to be conflicted. So this is a picture of a typical geostationary satellite. This is out in that very high orbit that sits in one place over the Earth. And all of those dishes are different antennas that are trained on different parts of the Earth. And there are treaties and agreements that say where that antenna can be pointed, how big its footprint can be, and how much power they can radiate in that spot. And we need to make sure everybody plays those. So Orus's mission was to map out the footprints of those satellites. So there's a little animation here. The red dot in there is Orus. Satellite is about this big, and it's in a low orbit, so it's going to go around the Earth about once every 90 minutes. Out here in the big green orbit is a geostationary communication satellite with 5 or 6 antennas. This is actually EchoStar 17, I believe, and it's landing those antennas on the Earth. The yellow ellipses are giving you the rough idea of where each antenna is landing on the Earth. So that represents their license. So there's no way to verify that footprint. You could take a car and drive all over the Earth with a power meter, or you could fly an airplane, but that's pretty hard to do. So the idea with Orus is it's just spinning around, and it just has a radio receiver, and it's recording its received power, its time, and its location. And as it flies through those yellow beams, it will then hear the beam and say, here's the power, here's the power, here's the power, and it'll fly back out. One lap through the beams is useless, but after days and days and days of going around through that beam, you end up with a map of the beam footprint of that transmission on the surface of the globe. So you can tell what that satellite was doing, and you can deconflict that. And then the idea, of course, let's not just do it with one. If you put a couple hundred of Oruses or Ori or whatever the right plural is out there, now you can form that beam map much more quickly. So this is a student-built satellite. It's very simple. It flies around, it has an antenna that's pointed at a geocomsat, and it records where am I, what time is it, how much power am I receiving. That's all it does. Downloads it to us when it's done. And from that, we put together the beam map like the one on the lower right. After a few hundred orbits or days or months, you now know a power footprint pattern on the surface of the Earth, and you can go back to that satellite operator and help them understand their vehicle. You can deconflict overlapping beams, or more importantly, you can find bad guys that weren't supposed to be transmitting somewhere when they are. So that's really what this is used for. So this satellite is being built right now by students at Michigan Tech. It's about the size of 4 loaves of bread. It's called a 12U CubeSat. Interesting. So the fundamental unit of CubeSats is a Beanie Baby cube. So a 12U CubeSat is the size of 12 Beanie Baby cubes. And this is 12 Beanie Baby cubes. It's kind of a very unsexy rectangle, but it's very compact. And if you actually look down the hall, if you go down here and take a right look in room 118, you can see the components of the satellite laid out there, what we call flat sat. So we take them all and lay them out flat so we can troubleshoot all the electronic interactions and software, see how it's working. This isn't manifested for launch yet. Likely it's going to go up in early 2025. We've got another design review to go through, and they're looking to allocate space for us now. One other one, Stratus. Stratus is an imager. It's the size of 3 Beanie Baby cubes, so a loaf of bread. It has an infrared camera that just points down. It does 2 things. One is it measures cloud cover. Just goes around and measures cloud fraction wherever it is. It's got an imager trained at the ground, and it's just measuring that cloud fraction over and over and over and over again. And the idea, again, hundreds of these would do an amazing job at giving you hyper-local weather forecasts. You would have the cloud position so accurately, you could figure out, should we go in the backyard for my daughter's wedding picture right now or wait till 3:30? Because you can map the clouds down to a city block or a single lot of time. The other thing it does is it gets cloud top height. It can come over a single point, take an image from this angle, from this angle. And from those 3 images, you get stereoscopic imagery, and you can put together the 3D structure of the cloud. So that's what Stratus does. It's also in the development and build phase. This is going to go up in an interesting way. This is going to get carried into orbit on a SpaceX Crew Dragon spacecraft. So this is a resupply to the International Space Station. Stratus is going to be packed up in basically foam, shoved in the cargo craft, bungeed to the wall. It goes and docks to the space station. The astronauts will take this out, undo the foam, put it in an airlock. The robot arm is going to grab it, aim it out to space, just give it a little nudge, and it's gone. So it's going to be very cool to have astronauts deploy this vehicle. Switching gears a little bit to the final topic, Orbion. So Orbion Space Technology is a local company. And I'll tell you about what we do, but first of all, the reason why it's in this talk. This is an old org chart, and that would mean for you to look at it and see names of people. But we have 50 full-time staff right here in Houghton. We've got 8 PhDs, a very deep technical bench, and here's where those folks are from. My co-founder was a former PhD student of mine, Dr. Jason Somerville. Our first employee was a former PhD student of mine, Dr. Jason Makala. Third one, former PhD student of mine, Dr. Rob Wasilewski. We went and pulled these people back to get the band back together and bring them here into Houghton. The hiring then grew. You'll even recognize now the directors, some familiar names. Conwell Recchi, the Recchi Hall just on campus is named after that. He's a shareholder and a director. John Rockwell, the Rockwell Mezzanine at the Michigan Tech Ice Complex. John is also on the board of directors. So this is why it's included in the Michigan Tech Talk. It's a separate, standalone, completely independent company, but we really mine the talent here at Michigan Tech and find a way to keep the students from leaving and bring students back. These are not all fresh hires. Many of these folks have been out in the wild for 20 or 30 years and found Orbion a way to come back with their families, with their hope, and contribute to what we do. So what do we do? So all these satellites are up there and they're not taking a limousine anymore. They're all riding a bus, right? 100 satellites pack on a rocket and they all split the fare and they get up into orbit and it's cheap for them. But when they get there, that's not their destination, right? They're at the bus stop and they've got an office to go to because they need to make some money. All of those satellites need their own propulsion to do it. And that's what we do. So we make xenon plasma thrusters. They're called a Hall effect plasma thruster. And each satellite has one, and the satellite uses it to maneuver in space as it will. So it uses it really for 3 functions. It goes from the bus stop to its office. Once it's at its office, it uses the thruster daily or weekly to either maintain the orbit, change the orbit, or getting more important, avoid collisions. Because there's so many other things out there, it has to step aside every now and then, come back. Then at the very end of the mission life, with sort of its last dying breath, the last propellant in the tank, it will use the thruster to intentionally deorbit the satellite so it burns up in the atmosphere, doesn't pollute space, and opens up a spot for another satellite. We just bought a new Orbion thruster to go up and earn its living. So it's a great recurring revenue. It's like painting the Mackinac Bridge. You start from one end, by the time you get to the other, you got to turn around and do it all over. So once you get a customer, you have them for a long time. We service not the smallest satellites because there wasn't enough market in them. Our satellites are what we call 100-kilogram class, so about the size of a dishwasher, maybe to a small refrigerator. That's what our customers are flying, and they buy our thrusters. This happened to be our field. I've done research here in plasma propulsion for 23 years now. So to me, I could see this coming, and to my co-founders as well. And this is one of the early plots we went out with, and this is another version of satellites launched per year. And you can see it ticking along at 150 or 200, and there's this one little uptick. And I went out a couple of years before that and tried to raise some capital. I said, this market's about to explode. Look at this great plot. Things are going to take off. This was some big consultant out of Europe that said, here's what the satellites are going to do. And nobody believed me. They said, market trends are not shaped like a hockey stick. They grow more slowly. You have no idea what you're talking about. Get the hell out of my venture capital. A couple of people believed in it, and I'm glad they did, because this is what the market actually did. So our timing was just about perfect. We saw the inflection coming, and we developed the technology before the demand was there. So we're hustling to get the tech ready as the customers are getting ready to buy it. And it's all been coming together in about the past year, where we have beating down our door and our product is ready and it's off the market. By the numbers, we've been founded for 7 years now. The first year or two was pretty lean, 2 or 3 guys and a napkin sketch. We've now grown to over 50 employees, all except 3 are full-time here in Houghton. So it's a bricks and mortar company. Very large technical team. 8 of us have PhDs. Everybody has a bachelor's, lots of masters, MBAs all over in there. We've raised $40 million in capital so far that's funded our growth and given us our legs while we now start to bring profit in. We've got over 40 systems sold to date, and we can produce, according to our facilities, about 1,000 units per year. Now we just need to add the folks to turn the cranks and make that happen. This is what our product looks like. We call it Aurora, after the Aurora Borealis. It makes a beautiful plasma from the north, so that's what we do. Over on the left are the 3 components. The one you see there, the Hall effect thruster, that was back in this picture here. That device right there is almost exactly the size of a coffee cup. So the thruster is only about this big. The power processing unit is a box of exquisite electronics that's about the size of a thick encyclopedia. And then the xenon flow controller is a set of valves that meter the xenon in there, and that's about the size of an iPhone. So those three things together make up the Aurora system, and they retail for about $500,000 per set. What we do then is we package them into custom configurations for our customers. They say, here's my satellite, here's the space I have. They then send us a piece of the satellite. We co-engineer the geometric orientation of the components, hook up the plumbing, hook up the cabling, send it back to them, and they drop it in their satellite. And then they are dependent upon us because we've inserted ourselves in their assembly line. They can't get from the start of the line to the end of the line without sending it to Houghton and bringing it back. We build everything here in Houghton except the circuit boards. So we have an AS9100D certified factory. That's the highest quality standard in the defense industry. This is just down the street at what's known as the powerhouse, right next to the bridge in Houghton. We also have a second facility up near Sharon Avenue that we call Evergreen, where it's more of our testing and development laboratory. We have giant vacuum chambers there, so we can take these thrusters, put them in the vacuum chamber, and take each one for a test drive before we deliver it to the customer. We've got tremendous facilities, control rooms that handle it all, vibration test facilities to make sure we can withstand launch environments, very accurate metrology for checking the conformance of our parts. And the picture there on the lower right is a completely integrated propulsion system with the xenon plasma coming out of it right before delivery to a customer. That brings us to the end here. I think this is a great place to do this business. I love this photo. This was in March of this past year. Inside the laboratory, we were running a development thruster on an exotic propellant called Krypton. So we're making Krypton plasma with the Aurora. And overhead of the laboratory outside in the Houghton sky was the Aurora Borealis, or Mother Nature was doing the same thing with oxygen and nitrogen. So where can you build plasma thrusters in a laboratory with the northern lights overhead? That brings to the end. I didn't open it up for any questions as we went, so certainly I sucked the air out of the room. So happy to take any questions here. Oh, thank you.
Yeah, xenon, all the stores, the pressure vessel, they store that in, I didn't think it could use cryogenic. That probably was
Yeah, cryogenic is hard to store because, as you know, as it warms up, it will boil off. So xenon is it's an amazing element. There's a couple of reasons we use it. The first is it is the largest atomic species that's not radioactive. It's on the lower right of the periodic table. So what that means is it's very easy to ionize. You don't have to waste much energy to steal the outer electron from it and turn it into an ion. The other thing we love about it, though, is it stores as a supercritical fluid. So the density of xenon in our pressure vessel is twice that of liquid water. It's about 2 kilograms per liter. So you can store a whole lot of xenon in one vessel, and it's not a liquid, so there's no free surface. It's not sloshing. It fills up the container completely. So it stores very, very densely, and that's one of the main features of it. So we load to 1300 psi at room temperature, and that because the spacecraft may get as warm as 50 degrees C. So at 50 degrees C, that makes it 2500 psi max expected operating pressure. So we buy tanks then that can do 2500 psi. So very modest pressure. And then the thing about it, because it's supercritical, if you wanted to put more xenon in there, you're tempted to store it at higher pressure. It doesn't really buy you much. You can triple the pressure and only get 5% more mass stored in the container because think of it as a liquid already. So at 1300 psi, there's no sense trying to shove more in there. So it's really nice trade-off. Dave started using Krypton because it's cheaper. The Ukraine issue really messed up the rare gas market. 30% of the world's xenon and krypton was made in the Mariupol steel plant as a byproduct of liquefying nitrogen and oxygen. So when the Mariupol steel plant was blown up, the prices of xenon and krypton went up by 20-fold. Krypton has always been an order of magnitude less than xenon. So the price of xenon got so ridiculous and it became so hard to come by. They're using krypton, which stores, much worse, 4 times the volume for the same mass of krypton, and its performance is worse as well. But in the interim, they've defaulted to that. And that was one of the reasons I showed you that we did a test on krypton. Our device works just as well on krypton as theirs. And if a customer is really trying to save a buck, they can load the tank with krypton instead of xenon. That it? Too warm in the lecture hall. It's never a good sign when your class has no questions and they're looking at their watch.
I got one for you, right?
Yes, sir.
So what's the next development in these kinds of thrusting?
I'd be jaded to say that there's not going to be a breakthrough tech development. When I was looking at forming the company, being a researcher, I really wanted to design the next mousetrap. You know, how can we do better? Is there a breakthrough out there? And I'm pretty convinced there isn't. There are low maturity technologies that if they work exactly the way you expect, they can have 10% performance improvement over a xenon Hall effect thruster. So after 10 years of scar tissue, it turns out to be worse. So it's really hard to justify that. I think the next step is what we're doing. It's manufacturability. Building one of these or 5 of these is okay, but we as a country need to be able to learn how to build these things like we build F-150s. We need to be able to build a few thousand a month and find the same reliability and the same quality that the auto industry has done. So I think it's in the more practical aspects of the tech rather than rocket science. Yeah.
So what are the compromise that you have to make for the small satellites corresponding to something which is like a base satellite?
First one is power. So these are our devices use electrical power to generate thrust. They take electrical power from the solar panels, they ionize the xenon, and they electrostatically shoot the xenon out the back end. So if you have more watts of power, you're going to get more millinewtons of thrust. And yes, I said millinewtons, because they're very low thrust devices. So at our location from the sun, in 1 square meter of space, there is 1,400 watts of solar power going through that. So that is the ultimate limit on the power you can harvest from a solar panel. So the smaller the satellite is, the smaller the square meters of your solar panels are, the lower the number of watts you can collect and power it. So this device works at about 200 to 300 watts, which is the amount of power that a 1 meter by 1 meter spacecraft can generate with small solar panels. So that's the main limitation. If we could get a small space nuclear reactor and do 5 or 10 kilowatts, then you would multiply the thrust of this by orders of magnitude. It's very straightforward. It's actually harder to design these small than it is to design them large. So the main limitation is power. Yeah.
Are the thrusters articulated so they can rotate and?
They aren't. So the big large satellites out in geostationary orbit that have been using this type of thruster for years, they do have gimbals on the thrusters and allow them to articulate. The gimbals are very expensive, very error prone, and they add a lot of mass. So the small satellite market is trying to find a way to minimize all of that. So all of our customers are doing a body fixed thruster. They're not using a gimbal or anything to articulate it. So it's incumbent on the satellite to point the entire satellite if it needs to change the thrust vector.
So how does it change its direction?
There's a couple ways to do it. So nope. So the most responsive way, you got a satellite floating in space. Inside of it is a flywheel on a motor. Spin the flywheel this way, you're going to go that way. Spin it back that way, you're going to go this way. So take 3 of those orthogonal, and now you can spin them up and rotate yourself in whatever direction you want. So that's the most reactive way to do it. Another way to do it is use magnetic torque rods. So there is, of course, a geomagnetic field out there, and something that's magnetized will torque on that field. The needle on your compass, right? The Earth's magnetic field puts a torque on it. So on your spacecraft, you can put 3 electromagnetic rods, and then as you energize them, torque off the Earth's magnetic field to get yourself in whatever direction you want. So those are the primary means, and those are great because they don't use any consumables. You're not thrusting anything, you're just using electrical power to spin a wheel up, spin it down, or a torque rod. So that's primarily how to do it. Yes.
Do you have competition or do you have the market?
We've got 2 competitors out there where it's hand-to-hand combat, and they are about the exact same maturity as we are. So that's the great thing. We didn't have to come in and elbow out a Boeing or something like that. It was a big blue ocean. Nobody was doing this. There was a huge demand coming for it. And now 3 of us is just about right. It's enough of a barrier that a 4th and a 5th company think twice. But there's sort of enough of it to go around. And so we compete with 2 other companies. Yes.
You can call it back there. Better call somebody's land trust more like a charge plate grid, something like a grid or something like that. Start grid.
Yeah. So what's traditionally known as an ion thruster. Think of it as an ion thruster as a coffee can, but the entrance has a screen on it. So you create plasma inside, and if an ion sneaks out of the screen, there's an electrostatic force that shoots it out and makes thrust. The problem with that is that screen is impeding the flow that you're trying to create, and the screen can erode. So a Hall effect thruster conceptually Picture the end of the coffee can, get rid of the screen and put a transverse magnetic field across that. That transverse magnetic field impedes ions from crossing it, but if they do cross it, the Hall effect kicks in. If you have a current flowing transverse to a magnetic field, it creates an electric field transverse to both. So that generated electric field is then what accelerates the ions out without having to put a screen there.
So, I know they had some NASA spacecraft with all those ion, but what was this type of
They were the gridded ion thruster, the older type, yeah. And those have benefits for some missions. They have higher fuel efficiency than a Hall effect thruster, but lower thrust. So on those missions, mass savings was everything. The difference between getting to the asteroid and not was 3 kilograms on the spacecraft. So the ion thruster could give them their savings at the expense of a longer mission, because as lower thrust, the Hall effect thruster could have gotten them more.
plus lower power?
That's right. Solar electric propulsion, when you're heading away from the sun, you're going the wrong way. Your power is just falling off day by day by day by day as you go out there. All right, well, I guess I can release you to go back out and eat and drink some of the good stuff. I'm happy to talk or answer questions as anybody wishes. So thanks for your time on a warm Friday in August.